Welcome back to Maths with Mr. Duffield. Had a special request from one of my IGCSE candidates with this exam question. Let's get straight to it. I'll read it out for you. A metal cube has sides of length 4.5 centimeters, correct to the nearest 0.5 centimeters. The cube is melted down and the metal is used to make small spheres. Each sphere has a radius of 3 millimeters, correct to the nearest millimeter. Work out the greatest number of spheres that could be made from the metal, showing you're working clearly. All right. Well, what's going on here? There's all manner of different bits and pieces to this question. There's rounding, there's bounds, there's volumes, there's thinking about what the greatest number of spheres, what does that phrase mean? Well, first of all, we need to figure out how do I work out the number of spheres that can be made from this metal, okay? And that is going to form basically the base, the kind of central structure that we're going to use to answer this question. Okay, to find out the number of spheres that I can make from the metal cube, well, I've got to work out the volume of the cube and then see how many times the volume of the sphere can fit in, effectively. That is a division. The volume of the cube divided by the volume of the sphere will tell me the number of spheres that I can make from the cube, the number of times the volume of the sphere fits into the volume of the cube. Now, as I said earlier, this stuff has been rounded. Length of the cube is 4.5 centimeters, correct to the nearest half a centimeter. The sphere has a radius of 3 millimeters, correct to the nearest millimeter. This stuff has been rounded, so this is about bounds. This question is about bounds. We're asked for the greatest number of spheres, given that we know that this stuff has been rounded. So, the greatest number, I want the number of spheres to be big. How do I make sure that a fraction, because this division is a fraction, that's what it is. How do I make a fraction big? What makes a fraction larger? Well, you should know that the numerator will need to be big to make a fraction big, and the denominator, the bottom half of the fraction, will need to be small in order for the fraction to be as big as it possibly can be. I hope that makes sense, because that's the main idea that we're using for this whole question. Okay, let's take a look at the cube. And let me sketch one here. Here's my little sketch of a cube. I'm going to physically represent what I've got here. It's not Pablo Picasso's finest work, but that doesn't matter. Its side lengths are 4.5 centimeters, correct to the nearest 0.5 centimeters. What does that mean? It's been rounded. There are a range of values around 4.5 that it could fall between. And the length of that range is 0.5 centimeters. That is what it means to round to the nearest 0.5 centimeters. So, what are the limits of that range around 4.5? Assuming even distribution. Well, that's between 4.25 and 4.75. Okay? Which one of those values am I going to use? Well, I wanted the numerator of this fraction to be big, i.e. the volume of the cube to be big. So I have to use, for this question, the largest possible value of the side lengths of this cube. Effectively, I'm going to consider this as a 4.75 centimeter cube. Okay? Actually, before I do carry on, because the sphere's radius is 3 millimeters, I might be tempted to convert this to be this in the same unit. It's going to make the maths easier later on. So what, 4.5 centimeters, or 4.75 centimeters, excuse me, that's the same as 47.5 millimeters, isn't it? There's 10 millimeters in every centimeter. So I can effectively consider this as a 47.5 by 47.5 by 47.5, oops, excuse me, millimeter cube. The volume of that is, indeed, 47.5 times 47.5 times 47.5. I have done this earlier. It comes out as 107,171.875. Saved myself a bit of time done the calculations before I started this video. Trust me, we're going to need to cut as much time as we can on this. This effectively gives me the numerator of this fraction. Now we've got to find the denominator, the volume of the sphere, okay? So there's a sphere. Don't know how to draw a three-dimensional object. Not very good at this, but that's okay. This radius, we've been told, is 3 millimeters correct to the nearest millimeter. So let's do a similar exercise. 3 millimeters here. It's been rounded. There's a range of values that 3 could be, and the width of that range is to the nearest millimeter 1 millimeter. So similar thing, 2.5, 3.5 are the ranges of values that it could be. We want the volume of the sphere to be small because of what we've talked about earlier. So I'm going to use the lower value, 2.5 millimeters. Okay? Now, to work out the volume of a sphere, you got to crack open that formula book of yours, yeah, and take a look inside the exam paper, because on the inside page you get given it. It's 4 over 3 pi of the radius cubed. In this case, 2.5 centimeters cubed, or millimeters cubed, excuse me. Again, I've done this earlier, saving us a bit of time. I end up with my calculator telling me 125 over 6 pi. You could round that if you want. I'm choosing not to because I want to keep everything as close to accurate as it possibly can be. Big over small, right? We know that this is the largest possible volume of the cube. We know that this is the smallest possible volume of the sphere. Let's divide them by one another. 125 over 6 pi. Nothing wrong at all with keeping the volume of the sphere like this. It's more accurate. If I work that out on my calculator, I get the number 1,637. There is a decimal on the end, but what is the question asking me? The greatest number of spheres that could be made from the metal. 1,637 down here, yeah, is the greatest whole number. There's a little bit of spare metal, but that's the greatest whole number of spheres that I can make from this division. I hope that makes sense. That's actually quite a complex question. There's a lot of stuff going on. There's volumes, there's fractions, there's rounding, there's making sure we know what to use in terms of the bounds. Am I using the upper or the lower bound? It was a good question to ask for help with. I hope it all makes sense, and I wish you all the best. And for goodness sake, submit your work on Teams. I'll talk to you very soon.